cut the beginning. The good thing about the streaming is that if anything goes wrong, everybody will get to the YouTube
I see.
easily.
Okay. How can I share my screen? Ah, share. Okay. I found it.
Cut
Great.
the beginning. The good thing about the streaming is that if anything, that's it. I'm checking that everything is going well with the YouTube.
Okay.
So we are already streaming. It's perfect.
Great. Is this working?
Yes. And then let's see the streaming. Yes, everything is okay. Okay. So let me record it in, and I don't need to record it because it's already in the streaming thing. Oh, okay. I can record it anyway. Admit, go to the cloud. Okay. So let me introduce our speaker today to our MaPhyAG seminar. He's Simon, you say it's pronounced, no? Simon,
It's
not
both
Simon.
fine. It's both fine. It's both fine.
Okay. Schirren, he's going to talk about orthosymplectic Higgs bundles, classically and virtually. Thank you very much.
Yes, hello everyone. Thank you, Marina, for the introduction and the invitation to the seminar. Yes, so I'm going to talk about Higgs bundles. I'm very sure that many of you are more an expert on these things than I am. In particular, I'm going to talk about Higgs bundles with orthogonal or symplectic structures. I call them orthosymplectic Higgs bundles. We are going to recall the classic theory on this, and then really define what are the orthosymplectic Higgs bundles here. And in the end, I try to give some outlook on virtual analog, which I mean how these orthosymplectic Higgs bundles appear in Donaldson-Thomas moduli space. So first I talk about Higgs bundles and spectral sheaves. So this is just a quick recollection on something that most of you know. And then I'm going to talk more about bundles and their duals and the ones with orthogonal symplectic structures. And then I going to explain a few connections to Donaldson-Thomas theory. So I'm going to keep the first few slides rather elementary. This is also maybe a good start to learn these things if you haven't seen them before. And you can always ask questions or interrupt or point out any mistakes I made. So yes, so our base is always going to be S with a polarization. And that base S is going to be either a smooth projective curve or a algebraic surface, also projective. And everything is going to be other complex numbers. So Higgs bundles for us are pairs E phi, where E is a vector bundle, and phi is an endomorphism on E twisted by the canonical sheaf on S. So by spectral theory, we all know that it is equivalent to Higgs bundle to give its spectral sheaf that I always denote as curly E phi on the total space of the canonical bundle. Basically, as you can see in the picture below, we have a sheaf that is supported on the eigenvalues of phi acting on E. And to these eigenvalues, we attach the corresponding eigenspaces. So the green picture here is the spectral surface inside the canonical. And to these, we attach the eigenspace. So, and the spectral correspondence says that the category of Higgs pairs on S is equivalent to the one of coherent sheaves of compact support on X. Yes, so that was spectral theory. So this slide is very full. I apologize for that, but I'm quickly going to state the main things that are going on here. So instead of phrasing everything in terms of vector bundles, we can also do this by phrasing it in terms of their frame bundles. So every vector bundle E on S is equivalently given by its frame bundle, which is a principal GL bundle on S. And if we go back to the original literature of Hitchin, and we want to study the moduli space of stable G bundles on S, so we have some stability condition here, and we do this via the symplectic geometry of its cotangent bundle. And close points of this cotangent bundle, Higgs bundles by set duality, because a close point is given by a stable bundle E, together with the dual of a deformation, which is by set duality just given by a Higgs pair, by a Higgs field. And so just going back to the frame bundle side, just as the principal frame bundle is a vibration by Lie groups, the deformation theory of phi is now governed by the Lie algebra, small g to g. And if we go one dimension higher, if we go to the projective surface case, and what we do is we take the moduli stack, M, all Higgs pairs on S, and they have a natural, which we call derived structure. And so we also have a derived structure on the so-called -1 shifted cotangent stack, which is a very mysterious object, but you can think of the stack as being the stack of all Higgs pairs on S. And we fix invariance in character of E and take the ones who are stable. And after removing the E star stabilizers, we get something here N, which is still a derived scheme, but the underlying actual scheme then has something that is quasi-smooth structure. And this quasi-smooth structure later on will endow it with a perfect obstruction theory, and then we get the virtual structure mentioned earlier. So the upshot is that we have, in the Riemannian surface case, we work basically with the cotangent bundle. And if we go one dimension up, we have this -1 shift cotangent bundle. So now back to the elementary things. We are interested in bundles that have a pairing. So by a pairing, I mean a map from the bundle E to its dual bundle. And if we now look at this bundle of homomorphisms, of sections of local endomorphisms from E to E dual, then those local endomorphisms, they fit inside this bundle. And since E is reflexive because it's a vector bundle, if we take F and map it to its dual, then the dual is also going to be in this endomorphism bundle. So if you take duals, that is going to be an involution on Hom EE dual. And you're going to have -1 eigensheaves of this involution. And the ones who are fixed, the +1 eigensheaves, +1 eigensheaf, consist of the symmetric sections. And the skew ones, the ones where the dual equals -f, are the ones that sit in the second summand here. So we get a splitting into +-1 eigensheaves. The first one are the symmetric ones, and the second summand are the skew ones. And now the first definition, we call E and Q, where Q is symmetric map and orthogonal bundle. And we call E omega a symplectic bundle if this omega is Q. So in the first case, Q sits in the first summand, in the symmetric one. In the second case, omega sits in the second summand. So yes, obviously that was the local picture I wrote up here, but then we want Q and omega to be globally defined on the local. And equivalently, those principal GLR bundles that we have, they are going to be of gauge group OR and SPR, so the orthogonal group and the symplectic group. So that means that we take the subgroups of GLE that preserve this symmetric or skew-symmetric form on E. So F, this automorphism now, preserves this form. This is what I wrote in this equation. And if you now look at the corresponding bundle of Lie algebras, then you will see that the Lie algebra to OE and SPE, which I wrote with like small so and small sp, they're going to satisfy this following condition here. That is something you can look up in Fulton's book on representation theory. I think I have a link somewhere. And they are going to satisfy this following equation. And the best thing is that if you now take a global map from E to its dual, then this map F intertwines phi and minus phi dual. So that means that, so let F be a non-degenerate pairing, isomorphism between E and its dual, then we get this identification simply by push forward of sections of this endomorphism bundle to Hom E dual. Now the Lie algebra, EE and SOE, they sit in this left-hand side in Hom EE. And they get, if F is skew, they get pushed forward to the symmetric maps. And if F is symmetric, then the orthogonal Lie algebra gets identified with the skew maps. Maybe you've heard the slogan that the orthogonal Lie algebra are skew maps. This is because orthogonal Lie algebra sitting in Hom EE with this identification between E and its dual gets identified with the skew maps. So again, 2 slides back, and we recall that EE dual has the splitting into plus minus 1 eigensheaves. And this first summand here is the one that we identify with SPE, and the second one is the one that we identify with. Now we can define what we mean by a symplectic Higgs pair. It's a symplectic bundle that we defined already. So E is a vector bundle and omega is U form, such that phi sits in the symplectic algebra. So if omega is skew, then phi is symmetric by what we just said. And orthogonal means we reverse the roles. So U is symmetric, and phi, orthogonal, is now a skew form. So this is why this is a little confusing. I repeat again, symplectic Higgs pair means that omega is skew and phi symmetric, and an orthogonal pair means that U is symmetric and phi is skew. So this is all a little confusing, but I think if you read it again, then you'll see that it's going to make sense. And the upshot is that you can phrase both symplectic Higgs pairs as well as orthogonal Higgs pairs 6 points of an involution. So if you write down this involution, so E phi gets mapped to E dual minus phi dual, then a fixed point of this involution is a commutative diagram. So a fixed point means there is an isomorphism, so there is an isomorphism between E and E dual that intertwines phi and minus phi dual. And we're going to see that we're going to distinguish between 2 cases, namely that in the first case is U, then we get symplectic Higgs pairs, and in the second case F is symmetric, and we get orthogonal Higgs pairs. So how do we find these orthogonal and symplectic Higgs pairs in moduli spaces? So we fix invariance, and now we assume we have a moduli space of these stable pairs, either on S, a projective curve, or projective. And we restrict to Giesecke stability here. So there are many problems of stability in this entire discussion. This is one of the reasons why I think this is not very well established, because this usual trick of saying slope stability equals Giesecke stability by assuming that rank and degree are co-prime doesn't work here. This is because this pairing between E and E dual is going to force the first chain plus to be 0. There's a slight generalization where you don't need to assume this. Using twisted Higgs bundles, I'm not going to go into that, but if someone is interested, I can definitely give some references. So the idea is we have a Giesecke stable moduli space. So the moduli space is an honest scheme, and we're defining an involution. So an automorphism on N whose square equals the identity. And this involution is just this involution I just wrote, namely I is mapped to I dual minus phi dual. And Then the fixed point, as I just said, are those diagrams here. And you're going to distinguish two cases. First case is we assume that F is skew, and then phi is going to be symmetric. And we end up with the symplectic component. Or in the other case, we assume that non-vanishing symmetric part, and then it is going to be symmetric. And the Lie algebra is going to be skew, and we end up with this. So the idea is very clear. If you, for a second, forget the technical stuff I said, you have a moduli space, you have this involution on the moduli space, and you take the fixed locus of this involution, that's a moduli space. And this involution, this fixed locus of the solution is going to have these two components. By components, I mean they're open and closed in the fixed locus. And one component, I'm going to try the symplectic Higgs bundles. So the automorphism group, recall that stable sheaves are simple. So there's a single element that defines the automorphism group of E. And in the first case, it's symplectic. So it's an automorphism between E and its dual that is Q. And in the other case, it is going to be symmetric because the automorphism between E and its dual is orthogonal. We get these two components. And everything I said applies to, your favorite moduli space for Higgs bundles. There's one important thing. So if you work in dimension 2, then we not only have Higgs bundles, but Higgs sheaves, by which I mean usually you need to take into account torsion-free sheaves. And then everything is much more complicated. And I'm not really sure if there is a good definition for orthogonal and symplectic here. The reason is that, maybe I say this in a few minutes. Right, because first I'm going to give the most easy examples, E2 and O2. So we have something concrete. So the good thing is that sp2 is a group you probably know already. It's just SL2. So if we have rank E equals to 2, then the symplectic group is just SL2. So just a linear group. What does it mean that E is SL2? It just means that the determinant of E is trivial. But determinant of E to be trivial means that we have a trivialization of this line bundle here, or its dual. And from what we've seen previously, that E dual is just a global nowhere vanishing section, trivial, map from E to E dual. So this trivialization is just the same as giving a skew form. And so sp2 bundles, just the ones where you have a trivialization of a determinant, that is your skew form, and your trace is going to be 0. Usual SL2 addition. So sp2 is just SL2, something we know. And slightly more general, in relative geometry, you very often these moduli spaces where you want to fix a determinant. And we call in general those moduli spaces where the sheaves have a fixed determinant, we call them SLR bundles. Although the determinant might not be trivial, but if we have this map to the Picard scheme, this just means we take a certain fiber. We fix a line bundle downstairs and we take a certain stairs. And then E has this fixed line bundle L as the determinant, and the trace is going to be. And this is very important Donaldson-Thomas theory because these invariants here that arise from there, they're called SUR instead of GLR. They UR and SUR. The SUR invariant is much more helpful to compute invariance than the normal invariant, but it's just the condition. SUR just means fixed determinant and trivial trace. And yes, the most prominent computations here are given by Tanaka-Thomas, where they compute invariance for moduli Higgs sheaves on projectives. This is the stable case, that's the first paper, and the semi-stable case, second paper, where they use Joyce wall crossing. So it was sp2, now we have O2, that's even simpler, because O2 bundles just split into direct sum of line bundles. They be isotropic lines. So if you, I'm always a big fan of easy examples. If you restrict to a single point, then E is a rank 2 vector space. And your quadratic form is just a quadratic homogeneous polynomial and is going to vanish on 2 lines. These lines are called, these isotropic lines are going to be dual to each other. That's always the case. So is the dual of L. So, and this is all your way. This is why you can see that O2 is just C star, because in the end, you're just parameterizing line bundles. Because once you know the line bundle, you know that E is just L plus its dual. And so I wasn't very precise about the difference between O2 and SO2. So the Lie algebras are the same. This is why I always draw the Lie algebra SO2. But you should think of SO2, in this case, using a certain orientation of E. So now you could write E, L plus its dual, or you could say it's like M dual plus M. And if you look at the corresponding trivializations of the determinant bundle of E, those two writings are going to have different sign. So trivializations are going to differ by a minus sign. So SO2 means, okay, I choose one description, namely L plus dual. And that's the orientation date here. So those SO2 bundles are just direct of bundles. And phi has now this diagonal form, where lambda is a global projection of Ks. So the moduli space is just this so-called trivial example. If you look at Hitchin's paper from 1987, stable bundles and integrable systems, he gives the first trivial example, he calls it trivial, for the Hitchin vibration. And yes, if you just have a line bundle and a section, you just get this like space here. So let's say that E is 0 and you just have degree 0 line bundles. You have the Jacobian. The Jacobian has trivial tangent bundle because it's a Abelian variety. So this is why this product space, the Jacobian, the tangent is the Jacobian. And yes, if S is a surface, I think you could see this as a -1 shifted. Have this shift. If you look at the cellularity here, this is how I like to think about this. I haven't seen it in literature, so. But if you look at the deformation picture, Higgs fields and Higgs bundles in then this is probably what you get. Right. So I wanted to close this section by describing the corresponding spectral sheaves in this case, and also giving a few pictures. So my favorite way of seeing spectral sheaves is by seeing them as this co-kernel of this two-step resolution. Basically, it's an old paper from Knudsen and Mumford, it's called Trace and Divisor. It says that the divisor class sheaf, in this case, it's E phi. Divisor class, this sheaf has a two-step resolution by local freeze, and the divisor class is going to be the determinant of this differential map. The determinant of this differential map here is basically the characteristic equation of phi on the fibers from X map to map. So E phi is just this co-kernel here. And now we want to see what is corresponding dual spectral sheaf. So the spectral sheaf of E dual minus phi dual. And what you do is you just go to the exact sequence and you apply the dualizing action. So then E phi 0 if you dualize it because it has to. And then you get a new co-kernel, and that's this X1 here. And that is I minus phi dual. After you do the following, so you first dualize the sequence, and then you -1 on fibers. Remember that in this involution gets mapped to minus phi dual. So you need to dualize first. And then you also need to apply a -1 action. And the -1 action on X is just the map that sends ST to S minus T. So in the spectral correspondence, that's going to send phi to -phi. So the spectral sheaf of -phi dual is just ED. So basically, it's the derived dual of the spectral sheaf. And then you are pulled back by this -1 on fibers. So if you look at this picture, then SL2 means -1 on fibers fixed on -1 on fibers. So SL2 sheaves are now fixed under this dualizing action and are -1 on fibers. So in particular, the trace is 0. So they are symmetric around the 0 section. This is just the condition that trace of phi is 0. And yes, so if you push down from the spectral surface to the base, then they're going to be self-dual. And O2, if you look at Hitchin's paper, then you're going to have these singularities or ordinary double points. And then your spectral sheaves looks like. In this case, these are the two sections you have. And they have this ordinary double point, this crossing. And one line bundle sits on one, and the dual sits on the other one. Right. So the upshot is we have this involution, E phi maps to E dual minus phi dual. And then the orthosymplectic Higgs bundles, so the ones who are either orthogonal or skew, they appear as components in this fixed locus of this moduli space. And if we go to the smallest non-trivial case, namely rank E is equal to 2, and we get the gauge groups SL2 and C star respectively. And if we want to write this in terms of spectral sheaves, we take the derived dual of the spectral sheaf and then pull back by this -1 on 5. And then the ones who are fixed under this action, they give us either SL2 so something that is difficult here, if you generalize this to projective surfaces, is the fact that E might not be a bundle if you take a moduli space Higgs sheaves on S. So it might be only torsion-free. These torsion-free sheaves are very important to people who do Donaldson-Thomas theory because very often you care about Hilbert schemes or nested Hilbert schemes. And then the easiest example here is an ideal sheaf of a point on a surface that is not going to be locally free, it's only torsion-free. So then this entire discussion is much more difficult because what is the dual of this? The dual here would be a complex because if you dualize the ideal sheaf of a point, then you get a complex, and this complex is going to have two non-trivial degrees. So one is just going to be a structure sheaf, but then you have an X1, and that is going to be the skyscraper sheaf of this point of this ideal sheaf. So if you dualize, you end up with a complex and not a single sheaf. So if you just work with moduli spaces for single sheaves, then it's not really clear what the dual is, and it's not clear what should be the meaning of an orthogonal or symplectic Higgs pair. So there is a simple trick. You can restrict to moduli spaces where you only have bundles, and then all of this makes sense. Of course, it would be nice to find a generalization, but it's not really clear how this works. Much more time. I do have much more. So yes, so now we go a little bit more into this Donaldson-Thomas area. So it's now going to be a projective surface, and we have this polarization. So what we do now, again, we have this moduli space, Higgs invariance of stable Higgs bundles. And by the spectral correspondence, that's the same as two-dimensional sheaves on the total space of the canonical, which in this case is a Calabi-Yau threefold. And since we are now working with sheaves on a Calabi-Yau threefold, it might be natural to think about Donaldson-Thomas related questions. So the tangent space for such a spectral sheaf is now given by x1. But we also have which are given by x2. And we call virtual dimension the difference, the x1 and the x2. And by Serre duality in the Calabi-Yau threefold case, this expected or virtual dimension is going to be 0. So although your moduli space is of the big dimension, in this computation, the expected dimension would actually be 0. So what we want to do now is we want to find the corresponding zero-dimensional cycle inside this moduli space of the correct virtual dimension. And we do this by looking at the virtual tangent bundle, which has now the right rank. So this virtual tangent bundle should have, in this case, rank 0. And that's also the case. So you take this R-Hom in E. So basically, this is just a complex that computes 1 and x2. And you choose a two-step resolution of this complex. And this complex over each closed point now computes deformations and obstructions. And this has rank 0 complex, yes. And I mentioned in the beginning that moduli space coming from the moduli stack of orthogonals have this smooth. The right moduli scheme has a quasi-smooth structure. And if we now restrict to the actual moduli scheme, it's underlying, then this is going to have a perfect obstruction. So this is the ingredient that is going to give us this virtual fundamental class degree 0 in our case. So this is just a map from this dual of this tangent, virtual tangent bundle, the virtual cotangent bundle, to this cotangent complex. And I think it's just important at this point to note that in this Donaldson-Thomas case, we don't work with a normal tangent bundle, but with this virtual tangent bundle or cotangent bundle. And in presence of a perfect obstruction theory, we get this virtual cycle whose degree is the rank of this obstruction theory. And the symmetry coming from Serre duality tells us that this rank is 0. So we actually end up with something we could count because it just consists of points. It's degree 0. And the existence of this perfect obstruction theory goes back to the famous Brent-Fontecchi, the intrinsic normal cone paper. Then in this specific setup, probably the best literature that really explains it is Albrecht Thomas. They say how to define a perfect obstruction theory for other spectrum. So since we want something compact, we need to go to the C-star fixed locus. So the moduli space has a well-known torus action, just mapping E phi to E lambda phi. So lambda is just the element of the torus, you just scale. And you define the virtual count by localizing to the C-star fixed. And what you do is you take this entire obstruction theory, which is the dual up here, and you restrict it to the C-star fixed locus. And now that is going to be too big, then the virtual dimension is going to be minus the dimension of the normal bundle. So you need to here. And this formula here is basically the Graeber-Pandrel C-star localization formula. So it basically tells you, given a perfect obstruction theory on N, how to define one for the torus. And that is your first that you can do. This counts inside this moduli space of sheaves on the C-star fixed locus. There are two branches of this locus, the monopole and the instaton. Maybe later on, if you have questions, I could say something about that. Yes, so either phi is 0 or phi is now potent. Yes, in the final few minutes, I tried to say a few things how we can use this to define similar invariants for other gauge groups. So this invariant we get here, we just, now I can go. So the invariant we had seen here is an invariant where we have not fixed the determinant. And it turns out that this invariant is useless unless these two cohomology groups here are going to be zero. And this has to do with the fact that we still have a Jacobian action on n. And these two things here, these two cohomology groups, they appear as direct summons in the deformation obstruction theory, and they're going to force this invariant to be zero. So it's much better if you pass through the QR locus. This is just basically SLR. Remember, that was just fixing the determinant and setting the tracer phi to be zero. So n has a map to this scheme, and you choose a line bundle downstairs and then restrict to a fiber. And then we reduce from UR to SUR by going to this submoduli scheme. And then the difficult thing is taking the obstruction theory in the big space and then defining it also. And it turns out that deformations obstructions, they split in this following way. So this means that the first summand is deformation obstruction with fixed determinant and trace zero. And the second summand is the deformation obstruction of the determinant. And the third summand is the deformation obstruction. And you get the perfect obstruction theory for SUR by just throwing away the second two summands. And you end up with a new virtual tangent bundle. And then this one gives you a much better account because now you have fixed the determinant bundle L, and you get better. So this original splitting and the corresponding obstruction theory was defined by Tanaka Thomas. And in our PhD thesis, we found a different way to explain this because there's another involution happening on this moduli space that is a little more difficult to see. But this involution is going to have summand as the fixed part, the second two summands as the moving part. And then again, you can see SU2 as a fixed locus of an involution. And then you get also the corresponding virtual tangent. So now how could we use this to define obstruction theories, virtual structure, symplectic moduli? We take the original obstruction theory, either UR or SUR, from Tanaka Thomas, and now define this involution that we did. So E phi is mapped to E dual minus phi dual, or using its equivalent form for spectral sheaves. And then we want to lift this involution to this perfect obstruction theory. So this is here what I said, we lift it to the equivariant derived category. So basically, we got this complicated diagram here that is more or less the dual of your obstruction theory. It's called the ITEA class, and if you modify it correctly, this is going to give you the perfect obstruction theory, basically by choosing representation for the side. And the idea is that you make this obstruction theory compatible with this involution. So I call this the virtual differential. So if you have an involution on any space, then this involution, the differential of this involution is going to act on the tangent space. And if you have a fixed point of this involution, then the differential of this involution is going to act on the tangent space entirely of this fixed point. And I call this the isotropy representation. And if it's an involution, you're going to have, again, plus minus one eigenspaces. And we do the same thing here. So we're going to lift this involution here to this virtual tangent bundle. And then we restrict to the corresponding component of the fixed locus. And then we take the fixed parts. So there should be a plus one eigenspace, basically the fixed part of this involution. And then this is going to give you a perfect obstruction theory of the fixed part, which is either going to be the symplectic or the orthogonal, the algebra group. So basically, you take this usual perfect obstruction theory, it gives you virtual counts. And then you also use this involution that gives you as fixed points orthogonal and symplectic bundles. You restrict this perfect obstruction theory to the fixed locus. And if you have an equivariant lift of iota, a virtual differential, to this perfect obstruction theory, then you can take fixed points here. And this fixed, well, let's say fixed part, and these fixed parts of the perfect obstruction theory give you a perfect obstruction theory of the fixed locus, which could be SPR or SO. So in this discussion, I chose SPR because we already know that SU2 is the same as E2. And here we already have well-established with obstruction theory. And with SOR, you had these problems with direct summons. So those objects are not stable always. So you need to be very careful what you do. But in SPR, you don't have these problems. And yeah, you're going to end up with a virtual cycle with the symplectic Higgs bundles. But you need to show again that this is going to be degree 0, which I think requires some more work that I haven't solved yet. And then it would be also nice to find out generalizations for other Chern classes, because this assumption that I made earlier when I said we take moduli space who only contain bundles comes from a big assumption on the second Chern class of E. So you choose this one to be minimal, and then this moduli space is to be only consisting of locally frees. And of course, it would be nice to find a better way. So there was recent work by Xinjing Bu. He defined orthosymplectic Donaldson-Thomas theory by using a moduli space of the complexes. And basically, your sheaves, locally free or not, you can always resolve locally frees. And then you can replace this sheaf by a complex of locally frees. And then obviously dualizing makes sense again, it's easier to do. But then everything is for complexes. And you need a different stability condition, perhaps Bridgen stability conditions. And the original Vafa-Witten theory, there are predictions for Giesinger stability. So this is why I try to stick to Giesinger stability, but there are some limitations here. And this is why I'm not so sure how much more generalization you can find in this in Thomas of authors. But yeah, it's so far it's an interesting project, and we will see what we can do with it. Thanks. I think this was the rest is literature. I can send around the slides, and if you want them, you can use the literature to get some more background and find the relevant papers. I just said yes.
Okay, thank you very much.
Thank you.
Thank you. Let me stop the recording. And is there any question? Armando, do you have any question?
Maybe yes.
Okay.
If I'm not wrong, on all these moduli spaces, you have a natural C-star action on the Higgs field. Is it right?
Yes, exactly.
So in the classical case, at the limit where the parameter is going to 0, you have a notch bundle. Okay?
What parameter?
I mean lambda x on Higgs bundle E phi, and you obtain E lambda phi. Okay?
Yes, yes.
Where lambda goes to 0, you obtain a notch bundle at the limit. Okay?
Okay, if you say so.
So my curiosity is in the case of the Hodge bundle, you are maybe there is some more stronger properties with respect to the general case.
I don't know much about this limit case. So for me, the cis direction was just a normal scaling action. And then you have two branches of the fixed locus.
Yes.
One is where phi is 0 and the other one where phi is null potent. And then, yes, you can study them. One is just like if phi is 0, you just end up with stable bundles E. And if phi is null potent, you get these nested Hilbert schemes in my case. But that's all that I know.
Okay. Okay, thank you. It's just a curiosity.
I have another question. The component, the connected component in this fixed point of of your involution are just these two ones, or are there any other ones?
Yeah, that's a very good question. Thanks. So there might be some other components that are not interesting because there is some intorsion of the determinant line bundle. So there might be other components, but there might be neither symplectic or symmetric. Then you just don't care about them at this point.
Okay.
So yes, I think if you look at fixed point, if we ignore phi and just look at a fixed point of E gets mapped to E dual, and then you look at the corresponding, then you take determinants of that, you're going to end up with that the determinant of E is going to be two torsion. Right. So there might be components where the determinant of E is two torsion, but not trivial. But those you ignore because they're not relevant for these gauge groups.
Okay. Okay.
So this is what you get.
Thank you.
Yeah. Yes.
Thank you very much. So thank
you.
Simon again.